Waste management.
Waste management is the generation, prevention, characterization, monitoring, treatment, handling, reuse and residual disposition of solid wastes. There are various types of solid waste including municipal, agricultural, and special. The term usually relates to materials produced by human activity, and the process is generally undertaken to reduce their effect on health, the environment or aesthetics. There is a wide array of issues relating to waste management, and those areas include generation of waste, waste minimization, recycling and reuse, storage, collection, transport, and transfer, treatment, landfill disposal, environmental considerations, financial and marketing aspects, policy and regulations, education and training, planning and implementation. Waste management practices are not uniform among countries, developed and developing nations, regions, urban and rural area, and sectors, residential and industrial.
History.
Throughout most of history, the amount of waste generated by humans was insignificant due to low population density and low societal levels of the exploitation of natural resources. Common waste produced during pre-modern times was mainly ashes and human biodegradable waste, and these were released back into the ground locally, with minimum environmental impact. Tools made out of wood or metal were generally reused or passed down through the generations. However, some civilizations do seem to have been more profligate in their waste output than others. In particular, the Maya of Central America had a fixed monthly ritual, in which the people of the village would gather together and burn their rubbish in large dumps.
Modern era.
Following the onset of industrialization and the sustained urban growth of large population centers in England, the buildup of waste in the cities caused a rapid deterioration in levels of sanitation and the general quality of urban life. The streets became choked with filth due to the lack of waste clearance regulations. Calls for the establishment of a municipal authority with waste removal powers were mooted as early as 1751 by Corbyn Morris in London, who proposed that, as the preservation of the health of the people is of great importance, it is proposed that the cleaning of this city should be put under one uniform public management, and all the filth be conveyed by the Thames to proper distance in the country. However, it was not until the mid-19th century, spurred by increasingly devastating cholera outbreaks and the emergence of a public health debate, that the first legislation on the issue emerged. Highly influential in this new focus was the report The Sanitary Condition of the Labouring Population in 1842 of the social reformer, Edwin Chadwick, in which he argued for the importance of adequate waste removal and management facilities to improve the health and well-being of the city's population. In the UK, the Nuisance Removal and Disease Prevention Act of 1846 began what was to be a steadily evolving process of the provision of regulated waste management in London. The Metropolitan Board of Works was the first citywide authority that centralised sanitation regulation for the rapidly expanding city, and the Public Health Act 1875 made it compulsory for every household to deposit their weekly waste in movable receptacles, for disposal, the first concept for a dust bin. The dramatic increase in waste for disposal led to the creation of the first incineration plants, or, as they were then called, destructors. In 1874, the first incinerator was built in Nottingham by Manlove, Elliott and Company Limited to the design of Albert Fryer. However, these were met with opposition on account of the large amounts of ash they produced and which wafted over the neighbouring areas. Similar municipal systems of waste disposal sprung up at the turn of the 20th century in other large cities of Europe and North America. In 1895, New York City became the first U.S. city with public sector garbage management. Early garbage removal trucks were simply open-bodied dump trucks pulled by a team of horses. They became motorized in the early part of the 20th century, and the first close-body trucks to eliminate odors with a dumping lever mechanism were introduced in the 1920s in Britain. These were soon equipped with hopper mechanisms where the scooper was loaded at floor level and then hoisted mechanically to deposit the waste in the truck. The Garwood load packer was the first truck in 1938 to incorporate a hydraulic compactor.
Methods of disposal. Landfill.
Disposal of waste in a landfill involves burying the waste, and this remains a common practice in most countries. Landfills were often established in abandoned or unused quarries, mining voids or borrow pits. A properly designed and well-managed landfill can be a hygienic and relatively inexpensive method of disposing of waste materials. Older, poorly designed or poorly managed landfills can create a number of adverse environmental impacts such as wind-blown litter, attraction of vermin, and generation of liquid leachate. Another common product of landfills is gas, mostly composed of methane and carbon dioxide, which is produced from anaerobic breakdown of organic waste. This gas can create odor problems, kill surface vegetation, and is a greenhouse gas. Design characteristics of a modern landfill include methods to contain leachate such as clay or plastic lining material. Deposited waste is normally compacted to increase its density and stability and covered to prevent attracting vermin, such as mice or rats. Many landfills also have landfill gas extraction systems installed to extract the landfill gas. Gas is pumped out of the landfill using perforated pipes and flared off or burnt in a gas engine to generate electricity.
Incineration.
Incineration is a disposal method in which solid organic wastes are subjected to combustion so as to convert them into residue and gaseous products. This method is useful for disposal of residue of both solid waste management and solid residue from wastewater management. This process reduces the volumes of solid waste to 20 to 30% of the original volume. Incineration and other high-temperature waste treatment systems are sometimes described as thermal treatment. Incinerators convert waste materials into heat, gas, steam and ash. Incineration is carried out both on a small scale by individuals and on a large scale by industry. It is used to dispose of solid, liquid and gaseous waste. It is recognized as a practical method of disposing of certain hazardous waste materials, such as biological medical waste. Incineration is a controversial method of waste disposal, due to issues such as emission of gaseous pollutants. Incineration is common in countries such as Japan where land is more scarce, as these facilities generally do not require as much area as landfills. Waste to energy, WTE, or energy from waste, EFW, are broad terms for facilities that burn waste in a furnace or boiler to generate heat, steam or electricity. Combustion in an incinerator is not always perfect, and there have been concerns about pollutants in gaseous emissions from incinerator stacks. Particular concern has focused on some very persistent organic compounds such as dioxins, furans, and PAHs, which may be created and which may have serious environmental consequences.
Recycling.
Recycling is a resource recovery practice that refers to the collection and reuse of waste materials such as empty beverage containers. The materials from which the items are made can be reprocessed into new products. Material for recycling may be collected separately from general waste using dedicated bins and collection vehicles, a procedure called curbside collection. In some communities, the owner of the waste is required to separate the materials into various different bins, for example for paper, plastics, metals, prior to its collection. In other communities, all recyclable materials are placed in a single bin for collection, and the sorting is handled later at a central facility. The latter method is known as single-stream recycling. The most common consumer products recycled include aluminium such as beverage cans, copper such as wire, steel from food and aerosol cans, old steel furnishings or equipment, polyethylene and PET bottles, glass bottles and jars, paperboard cartons, newspapers, magazines and light paper, and corrugated fiberboard boxes. PVC, LDPE, PP, and PS, see resin identification code, are also recyclable. These items are usually composed of a single type of material, making them relatively easy to recycle into new products. The recycling of complex products, such as computers and electronic equipment, is more difficult, due to the additional dismantling and separation required. The type of material accepted for recycling varies by city and country. Each city and country has different recycling programs in place that can handle the various types of recyclable materials. However, certain variation in acceptance is reflected in the resale value of the material once it is reprocessed.
Sustainability.
The management of waste is a key component in a business' ability to maintaining ISO 14001 accreditation. Companies are encouraged to improve their environmental efficiencies each year by eliminating waste through resource recovery practices, which are sustainability-related activities. One way to do this is by shifting away from waste management to resource recovery practices like recycling materials such as glass, food scraps, paper and cardboard, plastic bottles and metal.
Biological reprocessing.
Recoverable materials that are organic in nature, such as plant material, food scraps, and paper products, can be recovered through composting and digestion processes to decompose the organic matter. The resulting organic material is then recycled as mulch or compost for agricultural or landscaping purposes. In addition, waste gas from the process, such as methane, can be captured and used for generating electricity and heat, CHP cogeneration, maximizing efficiencies. The intention of biological processing and waste management is to control and accelerate the natural process of decomposition of organic matter. See resource recovery.
Energy recovery.
Energy recovery from waste is the conversion of non-recyclable waste materials into usable heat, electricity, or fuel through a variety of processes, including combustion, gasification, pyrolyzation, anaerobic digestion, and landfill gas recovery. This process is often called waste-to-energy. Energy recovery from waste is part of the non-hazardous waste management hierarchy. Using energy recovery to convert non-recyclable waste materials into electricity and heat, generates a renewable energy source and can reduce carbon emissions by offsetting the need for energy from fossil sources as well as reduce methane generation from landfills. Globally, waste-to-energy accounts for 16% of waste management. The energy content of waste products can be harnessed directly by using them as a direct combustion fuel, or indirectly by processing them into another type of fuel. Thermal treatment ranges from using waste as a fuel source for cooking or heating and the use of the gas fuel, see above, to fuel for boilers to generate steam and electricity in a turbine. Pyrolysis and gasification are two related forms of thermal treatment where waste materials are heated to high temperatures with limited oxygen availability. The process usually occurs in a sealed vessel under high pressure. Pyrolysis of solid waste converts the material into solid, liquid and gas products. The liquid and gas can be burned to produce energy or refined into other chemical products, chemical refinery. The solid residue, char, can be further refined into products such as activated carbon. Gasification and advanced plasma arc gasification are used to convert organic materials directly into a synthetic gas, syngas, composed of carbon monoxide and hydrogen. The gas is then burned to produce electricity and steam. An alternative to pyrolysis is high-temperature and pressure supercritical water decomposition, hydrothermal monophasic oxidation.
Resource recovery.
Resource recovery is the systematic diversion of waste, which was intended for disposal, for a specific next use. It is the processing of recyclables to extract or recover materials and resources, or convert to energy. These activities are performed at a resource recovery facility. Resource recovery is not only environmentally important, but it is also cost-effective. It decreases the amount of waste for disposal, saves space in landfills, and conserves natural resources. Resource recovery, as opposed to waste management, uses LCA, life cycle analysis, attempts to offer alternatives to waste management. For mixed MSW, municipal solid waste, a number of broad studies have indicated that administration, source separation and collection followed by reuse and recycling of the non-organic fraction and energy and compost fertilizer production of the organic material via anaerobic digestion to be the favored path.
Avoidance and reduction methods.
An important method of waste management is the prevention of waste material being created, also known as waste reduction. Methods of avoidance include reuse of second-hand products, repairing broken items instead of buying new, designing products to be refillable or reusable, such as cotton instead of plastic shopping bags, encouraging consumers to avoid using disposable products, such as disposable cutlery, removing any food liquid remains from cans and packaging, and designing products that use less material to achieve the same purpose, for example, lightweighting of beverage cans.
Waste handling and transport.
Waste collection methods vary widely among different countries and regions. Domestic waste collection services are often provided by local government authorities, or by private companies in the industry. Some areas, especially those in less developed countries, do not have a formal waste collection system. Examples of waste handling systems include: in Europe and a few other places around the world, a few communities use a proprietary collection system known as ENVAC, which conveys refuse via underground conduits using a vacuum system. Other vacuum-based solutions include the Metro Tafon, single-line and ring-line automatic waste collection system, where the waste is automatically collected through relatively small diameter flexible pipes from waste collection points spread out up to a distance of 4 kilometers from the waste collection stations. In Canadian urban centres, curbside collection is the most common method of disposal, whereby the city collects waste and/or recyclables and/or organics on a scheduled basis. In rural areas, people often dispose of their waste by hauling it to a transfer station. Waste collected is then transported to a regional landfill. In China, plastic pyrolysis or tire pyrolysis is the process of converting waste plastic tires into industrial fuels like pyrolysis oil, carbon black and hydrocarbon gas. End products are used as industrial fuels for producing heat, steam or electricity. Pyrolysis plant is also known as pyrolysis unit, plastic to fuel industry, tire to fuel industry, plastic and tire recycling unit, etc. The system is used in USA, California, Australia, Greece, Mexico, the United Kingdom and in Israel. For example, RESEM pyrolysis plant that has been operational at Texas, USA since December 2011, and processes up to 60 tons per day. In Taipei, the city government charges its households and industries for the volume of rubbish they produce. Waste will only be collected by the city council if waste is disposed in government-issued rubbish bags. This policy has successfully reduced the amount of waste the city produces and increased the recycling rate. In Israel, the Arrow Ecology Company has developed the Arrow Biosystem, which takes trash directly from collection trucks and separates organic and inorganic materials through gravitational settling, screening, and hydromechanical shredding. The system is capable of sorting huge volumes of solid waste, salvaging recyclables, and turning the rest into biogas and rich agricultural compost. The system is used in California, Australia, Greece, Mexico, the United Kingdom and in Israel. For example, an Arrow bioplant that has been operational at the Hairia landfill site since December 2003 serves the Tel Aviv area, and processes up to 150 tons of garbage a day. In Saudi Arabia, there is the world's largest AWCS now being built in the vicinity of Islam's holiest mosque, Mecca. During the Ramadan and Hajj, 600,000 kilos, or 4,500 cubic meters, of waste is generated each day, which puts a heavy demand on those responsible for collecting the waste and litter. In the Metro Tafon automatic waste collection system, the waste is automatically collected from 74 waste feeding points spread out across the area and then transferred via a 20-kilometer pipe network to a central collection point, keeping all the waste collecting activities out of sight and below ground, with a central collection point well away from the public areas. In San Francisco, the local government established its mandatory recycling and composting ordinance in support of its goal of zero waste by 2020, requiring everyone in the city to keep recyclables and compostables out of the landfill. The three streams are collected with a curbside fantastic three-bin system, blue for recyclables, green for compostables, and black for landfill-bound materials, provided to residents and businesses and serviced by San Francisco's sole refuse hauler, Recology. The city's pay-as-you-throw system charges customers by the volume of landfill-bound materials, which provides a financial incentive to separate recyclables and compostables from other discards. The city's Department of the Environment Zero Waste program has led the city to achieve 80% diversion, the highest diversion rate in North America. While waste transport within a given country falls under national regulations, transboundary movement of waste is often subject to international treaties. A major concern to many countries in the world has been hazardous waste. The Basel Convention, ratified by 172 countries, deprecates movement of hazardous waste from developed to less developed countries. The provisions of the Basel Convention have been integrated into the EU Waste Shipment Regulation. Nuclear waste, although considered hazardous, does not fall under the jurisdiction of the Basel Convention.
Benefits.
Waste is not something that should be discarded or disposed of with no regard for future use. It can be a valuable resource if addressed correctly, through policy and practice. With rational and consistent waste management practices there is an opportunity to reap a range of benefits. Those benefits include economic, improving economic efficiency through the means of resource use, treatment and disposal, and creating markets for recycles can lead to efficient practices in the production and consumption of products and materials, resulting in valuable materials being recovered for reuse and the potential for new jobs and new business opportunities. Social, by reducing adverse impacts on health by proper waste management practices, the resulting consequences are more appealing settlements. Better social advantages can lead to new sources of employment and potentially lifting communities out of poverty, especially in some of the developing poorer countries and cities. Environmental, reducing or eliminating adverse impacts on the environmental through reducing, reusing and recycling, and minimizing resource extraction can provide improved air and water quality and help in the reduction of greenhouse emissions. Intergenerational equity. Following effective waste management practices can provide subsequent generations a more robust economy, a fairer and more inclusive society and a cleaner environment.
Challenges in developing countries.
Waste management in cities with developing economies and economies in transition experience exhausted waste collection services, inadequately managed and uncontrolled dump sites, and the problems are worsening. Problems with governance also complicate the situation. Waste management, in these countries and cities, is an ongoing challenge and many struggle due to weak institutions, chronic under-resourcing and rapid urbanization. All of these challenges, along with the lack of understanding of different factors that contribute to the hierarchy of waste management, affect the treatment of waste.
Technologies.
Traditionally, the waste management industry has been slow to adopt new technologies such as RFID, radio frequency identification, tags, GPS and integrated software packages which enable better quality data to be collected without the use of estimation or manual data entry. Technologies like RFID tags are now being used to collect data on presentation rates for curbside pickups. Benefits of GPS tracking is particularly evident when considering the efficiency of ad hoc pickups, like skip bins or dumpsters, where the collection is done on a consumer request basis. Integrated software packages are useful in aggregating this data for use in optimization of operations for waste collection operations. Rear vision cameras are commonly used for OH&S, occupational health and safety reasons, and video recording devices are becoming more widely used, particularly concerning residential services.
Central principles of waste management.
There are a number of concepts about waste management which vary in their usage between countries or regions. Some of the most general, widely used concepts include 1. Waste hierarchy. The waste hierarchy refers to the 3 Rs: reduce, reuse and recycle, which classify waste management strategies according to their desirability in terms of waste minimization. The waste hierarchy remains the cornerstone of most waste minimization strategies. The aim of the waste hierarchy is to extract the maximum practical benefits from products and to generate the minimum amount of waste. C. Resource recovery. The waste hierarchy is represented as a pyramid because the basic premise is for policy to take action first and prevent the generation of waste. The next step or preferred action is to reduce the generation of waste, that is by reuse. The next is recycling, which would include composting. Following this step is material recovery and waste to energy. Energy can be recovered from processes, that is landfill and combustion, at this level of the hierarchy. The final action is disposal, in landfills or through incineration without energy recovery. This last step is the final resort for waste which has not been prevented, diverted or recovered. The waste hierarchy represents the progression of a product or material through the sequential stages of the pyramid of waste management. The hierarchy represents the latter parts of the life cycle for each product. 2. Life cycle of a product. The life cycle begins with design, then proceeds through manufacture, distribution, use, and then follows through the waste hierarchy's stages of reuse, recovery, recycling and disposal. Each of the above stages of the life cycle offers opportunities for policy intervention, to rethink the need for the product, to redesign to minimize waste potential, to extend its use. The key behind the life cycle of a product is to optimize the use of the world's limited resources by avoiding the unnecessary generation of waste. 3. Resource efficiency. The current, global, economic growth and development cannot be sustained with the current production and consumption patterns. Globally, we are extracting more resources to produce goods than the planet can replenish. Resource efficiency is the reduction of the environmental impact from the production and consumption of these goods, from final raw material extraction to last use and disposal. This process of resource efficiency can address sustainability. Polluter pays principle. The polluter pays principle is a principle where the polluting party pays for the impact caused to the environment. With respect to waste management, this generally refers to the requirement for a waste generator to pay for appropriate disposal of the unrecoverable material.
Scientific journals.
Related scientific journals in this area include Environmental and Resource Economics, Environmental Monitoring and Assessment, Journal of Environmental Assessment Policy and Management, Journal of Environmental Economics and